Hey gamers, Six here again with the first devlog update for Scorch's return. This last month, I've been focusing on developing a few dynamic AI systems. My goal for these systems was to have one set of systems which I can reuse for all of my AI in the game. To do this, I knew I needed two systems, one for decision making and one for moving around the level. I started with decision making, as I already had a prototype system using goal-oriented action planning, or GOAP, thanks to a tutorial I had watched a few months ago, link in the description. For example, let's cover a simple AI with only two options, moving and being idle. Let's say it's currently idle. It'll go through its possible goals and remove any which are already satisfied. For instance, in this case, it would check the outcome of the stop moving goal, which is idle, but because it's already idle, it will remove that as an option. For our other goal, move to random, the output is moving, and because the agent is not currently moving, it will remain as a possible goal. Since those are all the goals this agent has, it will now sort the remaining goals by priority. However, that'll have no effect in this case because there's only one goal left. Starting with the highest priority goal, it'll try and find an action that fits the appropriate effects for the previous point on the tree. If we look at the stand idle action, it doesn't have the appropriate effect. In order to connect to its parent in the tree, in this case our goal, move to random, it needs to have the goal's preconditions as its effects. This action, stand idle, has the effect idle, but not moving. Therefore, it cannot connect to the goal. Our other action, random patrol, has the effect moving, so it can connect to the goal. Random patrol would, for example, have no preconditions, and therefore it could be directly connected to our current state no matter what that state is. Of course, this is not a requirement. You might have other preconditions for that one as well, but in this case, there would be no preconditions, and so it connects. For our example agent, this is a valid pathway. And unless it can find a cheaper pathway, this would be pushed into the action plan, causing our agent to patrol randomly. However, I wasn't happy with this prototype. When I originally used the tutorial, I made slight modifications to prevent the need to rewrite code by making the GOAP agent class abstract. This way, each agent could inherit from it and implement independent functionality. However, this still required me to write custom code for each agent type. Imagine, for instance, we're creating the Super Mario Bros. And we want Goombas and Koopas. Each of these enemies would need to be custom programmed, but I want a system in which one brain could be reused for all of my agents no matter what behavior I give them. In other words, my goal was to create a brain which could create both a Goomba and Koopa behavior with the exact same programming. So I took the system that I built from GitMS tutorial, again, linked in the description, and I adjusted it so that each agent action was a mono behavior on the game object. This way, the agent actions could be customized on each agent without modifying the code of the agent's brain. That wasn't enough, as I needed another similar solution for my beliefs too. So I created an interface, iStatBelief, which is for any beliefs that are based around a statistic, such as, for instance, the current health, or checking if the agent is currently moving, as both of those could impact the behavior of the agent. The interface contains a public property which evaluates to find the Boolean value of true or false. Now, I'm able to create multiple different brain combinations using the exact same code, exactly what I was looking for. Honestly, I didn't entirely understand the GOAP framework when I initially built it. However, thanks to this refactoring, not only does it far better suit my needs, but I have a proper understanding of how it works. Now that I had a decision-making system, I needed a system for moving my agents. For testing, I had initially started with just moving the agents left and right, much like a Goomba. However, I knew that wouldn't work for long. What would happen when my agents needed to jump up or fall down a ledge? Of course, that would be needed later in development, so I needed to plan for this. So, I began working on a custom implementation of the A-star pathfinding algorithm. The reason I couldn't use a pre-made solution is that Scorch's Return isn't a top-down game, and any pre-made solutions I knew of were top-down solutions. And that's an important distinction because in a top-down game, it's all walking connections, but because this is a side view, my agents will need to jump or fall, which would require different types of movement than simply walking. I started with a navigation system scriptable object. This would store my graph of nodes and connections, utilizing the flyweight pattern, to prevent using extra memory to store the same data multiple times. Now, I can create multiple systems for a single level if I have multiple enemy types, and they can be set with different movement data, and one may be able to make jumps that another cannot. As far as creating it, I'm using an inspector button, which will scan the level looking for the appropriate layer masks to determine what is ground, wall, or air. Now that we have nodes, we need to connect them. I'm using a platform system in which I load my nodes into platforms. Each platform is exactly what you'd imagine, a set of nodes which all exist on the same ground object in-game. With this, my agents could move side to side on a platform, but they wouldn't be able to move up or down between the platforms, so I needed to connect those as well. This is where the system got tricky, as I wanted to use physics for my jumping. I decided to write kinematic formulas which I could use to find an array of positions along a trajectory. Then, I would send in the appropriate data from the navigation system, and I would check the returned points by line casting between them. If the line cast hits something before reaching the final point, then the system fails and the jump or fall is not possible and won't connect. However, if it does make it to the final point, it will create a bridge between those nodes. My bridges, of course, do have a value on them to determine what type of connection they are so that my agent mover can take an appropriate action from it. So if that connection is to walk, it will walk. If it's jump, it'll jump. And if it's fall, it will fall. However, because of the way that I'm currently jumping, I can actually use that for my falling as well. It doesn't sound like it should work, but it actually does, and it works quite well. I don't know though, maybe someday in the future we'll have it changed to where it walks off the edge instead of jumping down. Now that my graph is built, I just created an A-star agent which would search through the nodes based on the lowest F cost, just like a standard A-star agent. I'm fully aware that at this point in time, the system has many flaws and is not perfect, but it works for now as a prototype, and that's all we need. After all, I'm sure I'll come back later on to fix the problems that arrive when the agent is told to follow a moving object. However, for now it works enough, and that's what matters. Anyways, that's it for this update. If you want to keep up with the devlogs, make sure to like and subscribe. I'm so excited to see you next month, because next month's development will be very significant to the final game.